All right. One of the things I found out while we were on break was that there's an error on here which we better get corrected right away. When I was working on this graph, I was outlining which of the two, or which of the third level sets covered which second level sets or clusters. And I made a mistake right here. So you can see from going to the other diagram over here, 303 has 202 and 204. So on this one, I should have made this line go from here around this way to pick up 303. Common problem when you do these things. All right, now, having corrected our error, let's take a look at the last of our subject areas for this first ordering complexity session, and that's multivariable relationships. What we're trying to do is develop a sophisticated means of understanding the order implicit in a collection of problems or a collection of elements of some kind. Everything we've looked at before has been of the simple nature, first cousin of, or that kind of simple thing, even is used with, or is often bought at the same time as. These are all very simple ideas. What we'd like is to be able to extend the complexity of our notion of the relationship to any level of sophistication we'd like. So I'm going to suggest that we look at the idea of similarity. And let's start it out by putting up our title here, Multivariable Relationships. And then, under that, let's talk about similarity. That's a very general term also. We say something is similar to something else. What do we mean? It means that we've picked out some collection of aspects that two things seem to match up on. And that can be very a small set of aspects that we choose. I could talk about people and say that two people are similar if they're the same height. That's reasonable. But normally we don't do that. Normally we kind of integrate a number of things. And what we're doing is we're categorizing based on these properties that we're talking about. So let me put that up here as an idea. Categorization. That's what we're going to try to do. It's going to get our clustering working here for us on similar, better put that up, similar properties. What we're saying when we use similarity, if I can go back to our earlier terms, that the relation is similar to. And that is about as fuzzy as we can get, because similar, as I started to say earlier, could be many, many things. It can be a simple set of attributes or properties. It could be a fairly complicated one. We use it intuitively very well. When we go through, that's how we organize our life, really. We are constantly putting things in piles based on their likeness in some sense, so looking for some associative qualities. And is similar to is really what we're working with. But we can use it much more carefully to develop a notion of relationship, which we can test for things, where we can be even in looking at the same set of things, the same set of ideas, over a large number of variables for the large number of elements in a set. Why would we want to do things like that? Well, typically we might want to organize products on some basis, get some insight into them. A set of visual display terminals might be a good example. If we were to ask whether visual display terminals were similar, what would we be looking at? In terms, we would go back and pull out those kinds of things that count for us. Some of those might be what? Resolution. A couple of terminals would be considered similar if they have the same or very close resolution. What would be some of the other things we might look at? We might look at phosphor colors. If we're talking about a problem of marketing where cost is an issue, maybe excuse me, we might need cost as an issue in this thing. And we can go on. We can add a whole lot of these variables. And what we say now is that two visual display terminals are similar if they're similar on a number of variables. If over the collection of variables we looked at, they tend to come up with the same answers. And think of this almost as a set of questions on a questionnaire. If they tend to come up with the same answers over a fair number of questions, we say they're similar. And we can choose these things according to how we want to set up a study. So what we're looking at really is the ability to put a lot of questions in a questionnaire and use that to decide what similarity is. Now, similarity can be expressed simply in mathematical terms as the number of matches that you have on these various questions against the number of total questions that you have. What we call a simple measure, when this came out of numerical taxonomy, which is derived from the biological sciences field, the simple measure S for similarity equals M over M plus U. And that simply means M, the number of matches, and U, the number of non-matches or mismatches. The reason we bother to put it in these terms instead of just saying the number of matches over the total number of variables we're talking about is that in some cases we may not be able to answer a question for one of the pairings of our vertices or elements in this case. And so we may have some blank data. And so we usually actually add up the number of non-matches and the number of matches, and then they may be, for any given pairing that we're looking at, we may be not quite have the same number of questions that were answered as some other one, but we'll still get a value. The value will come out somewhere between 0 and 1. And so if you have a 1.0, that would mean that similarity is complete for any given for the pair we're looking at. If you have a 0, that means there's absolutely no similarity, and anything in between will be some value. Now, let's take that and look at it a little more with a little more enhancement. This is the simple measure. We've got this built into a computer program, and we're going to be able to use it, but we're going to also be able to use some other features. First of all, we can look at different kinds of data types. There are three kinds that we will normally use: discrete, rank order, and continuous. Now, when I say these are data types, actually these are the questions on the questionnaire we'd set up. These are the variables that we'd look at for looking at multiple variables. Discrete is if we have discrete data, you can either have a match or you can have a non-match, and that's all there is to it. Discrete data is that kind of question which says, what's the color of eyes, blue or brown or gray, and you have no idea what the ordering is. There isn't any ordering. You're either in one or you're in the other, and that's that. Now, it's a useful kind of question to ask, because many times we're really just looking at little pots to put things in, categories, and if two visual display categories, well, take phosphor, for example. That would be an example of that. We might have one which was, we're getting a white on black, and another one we're getting a green on black, and another one where we're getting orange on black. Now, what's the order? No order. But if they have the same phosphor, then in some sense they're similar. So discrete is valuable to us. We need it as a means of filling in one of the kinds of questions we might like to ask. Rank order is more obvious to everyone. That's the sometimes always never business, where you can associate things in some kind of order, though you may not know exactly where they fit on a scale. And continuous is that kind of data which fits nicely on a scale. Something like cost, for example, fits there very well. We know exactly what $10 is against $5, what 10,000 is against 5,000. We can fill in any degree of resolution in there that we like. So these are the three kinds of data that we have. We can do matches on this one or non-matches. But on these, we can do the same thing or more. We can do partial matching on here. We can say they're close, and we can be more specific how close they are. So partial matching is possible with rank order and continuous. Let's just take a little bit of an example here to kind of fill this out. Here are some possible variables we might set up. Say we're looking at comparing chairs. We're going to do a study on chairs. We're going to try to get a graph of chairs which will tell us, with clusters, we can find chairs which are similar to each other. So maybe the first question we want to ask has to do with primary use. And so we set up a set of possible answers to this. The first answer might be lounge or reception, rather. That's a possible use for a chair, and we see a lot of chairs that are designed pretty much for that purpose. Another one might be office or institutional. Different kind of chair. And a third one might be industrial, again a different kind of chair. Now what kind of a data type would that be? Well, it would be discrete data type, because we can't really say that industrial is any better or worse, or higher or lower, or more important, or there's no ordering that we can apply to any of these three. So it's just a categorization, and that's the discrete type of data. Another question we might ask in our study would be something about comfort. And we might set it up like this: comfortable. Give that our number one choice. We might say acceptable. And we might say uncomfortable. And that, of course, is a rank order question, because these are in order. Comfortable is on the top and uncomfortable is on the bottom, acceptable is in the middle. Finally, we might put another one in just for an example here, which we can use for continuous data: cost. Cost is, you might just put in the actual value in this case, so we don't have to set it up. We can set these up as questions with answers on them and use the numbers directly in the computer program. With cost, we can just put the actual amount of money in. And similar other kinds of continuous data. If you're doing a study on automobiles, perhaps you want to put in horsepower, and the actual value goes right in. In terms of our visual display terminal back here, this would be a continuous data type. Resolution would probably, depending on how we set it up, it could be rank order, it might be continuous. I have to think about how we do that. Phosphor colors would definitely be discrete. All right, so that's one thing that we can do. It gives us a little more possibility. It kind of opens up the way we can treat our variables. Another thing that we want to be able to do is what I started to say right here, and that's partial matching. So let's look at that. Shouldn't have to have just complete matches when we look at this data. We ought to be able to say, well, it's close. It's closer than that kind of pairing, so perhaps we ought to be able to say, instead of being 0, no match, 1, complete match, maybe we ought to say a half, sort of in between, or a third, or a quarter. And that would be what we call partial matching. We do that by setting up a match difference and a no match difference, which we can describe for each individual, did I spell out difference? Yeah, nope, got an E in there, gotta watch that. For each individual one of our variables. Now a match difference, and I'll put in some definitions here because this tends to get a little bit confusing. That would be the maximum difference for a complete match. What that means is, how large can the difference be before we want to say, well, it's no longer a complete match. Maybe it's a partial match, but it's no longer a complete match. It means we can allow some little flexibility, some tolerance in there. So you don't have to have it exactly on, and things don't have to be exactly the same cost. For example, we could maybe accept a $2 difference and say, it's still the same. We'll call that a complete match. On a no match difference, we're talking about the other end of the same problem. And that will be the minimum difference for a complete mismatch or non-match. And what we're saying here again is, how far apart do they have to go before we don't think there's any partial matching? They're completely non-matched. To give you a little more visual demonstration of that, let's set up a little scale here, and I'll just put some numbers on it. So I'll say this is 0, 1, 2, 3, 4, 5, so on. And we'll call this, we'll take a look at, say this is a cost variable we're talking about, and this will be a difference scale. And so let's say that we have a match difference. We're talking about some chairs now. And we'll say the match difference is $2. Sounds like a kind of a small difference, but I'll do that anyway. And let's say that the no match difference is $5. Now what that means is, if they differ by 2 or less, it's going to be a complete match. If they differ by 5 or more, then it's going to be a complete mismatch. Now if we look at that on the scale here, and let's say this is a difference scale. Then what have we got? We go right here. Here's the match difference. I'll just fill this in, hatch it in like this, and say that's the complete match. That means that $2 or less difference, I don't care, maybe we're talking about a chair that costs $18 and another one that costs $20. They would differ by 2, we'd say they're still completely matched. Now if we come over here to the $5 part and do a little hatching over here, now what we're saying is that this area, and that goes on out forever, is a complete mismatch. Which means that, of course, that if they differ by 5 or more, there we don't count that at all. Now what's left is this interesting area right in here. And this is where the partial matching is. So with this given, that would mean if they differ by $3, what would we have? Anybody? A 2/3. That's a 2/3 match, right. If they differ by 4, it'll be a 1/3 match, and of course 5, and we're back down to 0. You can see here it's 0, no match, in other words. Up here, this is 1/3 of a match, 2/3 of a match, complete match, all the way on this way. So this is a rather nice addition to our scheme, where data types help us a lot, but being able to do partial matching gives us a great deal of control. We can take any individual variable and decide for the study that we're working on just exactly how much we want to allow, what kind of tolerances we want to allow for matching and non-matching. One other thing that we can do, and this is added again as an enhancement here, our number 3 enhancement to our system, is weighting. That means that we can set up different emphases for different strategies. Now I'll have to explain that one a little bit. For example, let's say, and this is a real example, it's one we did for J.C. Penney. But let's say that we're trying to look at stores and the design of a store and the organization of the merchandise in the store. J.C. Penney, like Sears and other major stores of that kind, have to figure out where they're going to put all that merchandise. They have so many different kinds of merchandise that since they cover a full range, that it's not an insignificant problem. Now let's say we were trying to do that. What we actually did here was we set up a set of variables which looked at things like who buys the product. And we talk about they're almost always women, almost always men. We looked at how the product was maintained, how it was picked up, seasonal variations. I think we came up with about 70 different variables that we examined and tested our merchandise types on. And the idea was to find those kinds of merchandise that were similar so we could put them in the same place in the store. And when you get back to those diagrams like we had over there, you begin to see how the store lays out in terms of its merchandise islands and the places where they go, where the merchandise goes. Now the interesting thing is, that related to our weighting problem, is that the store changes depending on where it is. If it's a store in a mall out in the countryside, part of great suburbia, it probably is a store which has a lot to do with recreation, because that's what the modern recreation activity. People go out to a store and spend 3-4 hours just kind of wandering around, not only buying merchandise, but just kind of seeing what's going on, talking to people, and just generally enjoying themselves. The old market in modern times. If it's in the big city, it probably is operating in a different way. It's probably more convenience-oriented. People are stopping in at noontime or right after work, picking up things that they need and going on. Two different strategies for how you would organize a store for two different reasons, a different kind of place, different kind of context. Now what we can do as weighting is we can take the same set of variables and decide whether they're more important in this kind of a strategy than others, or whether they're less important. And if we're talking about a mall operation, then some of these are more important than others. If we're talking about going downtown, a different set will probably be more important. So we can put weights on the variables, and then how they determine the closeness of any given kinds of merchandise will be controlled partially by our interpretation of whether they're important or not in the strategy of the store. Now you can do this for a lot of other things, and that gives us a great deal more flexibility. That plus partial matching is probably the key to our real flexibility in this relation program. So now let me say a little bit about what the relation program does without actually getting into it in too great detail here. We're going to talk about it a little bit more in part 2 of this talk in terms of what it does in the specialized program for design and planning. But basically it is this. It is a program called relation. 6 letters or less, right? So we drop out a few. And it stands just for that, relation. It calculates the amount of relationship. And it does that on that 0 to 1 basis for pairs of elements. And it uses, and this is an interesting part of it here, it has available to it 3 similarity measures, the one I told you about, and 2 variants on that, which allow you to make a greater separation at the high end or the low end of similarity if it turns out that things tend to be either very similar or very dissimilar. But chances are you use the S equals M over M plus U. And then it has an additional 18 interaction measures. And interaction is a very interesting concept too, as we'll see in a minute, which again has a great deal of possibility for general purpose work, most of which is not even explored. This is a measure which I developed here at IIT about 6-7 years ago, and we really haven't had a chance to explore completely, but it is designed primarily for work in design and planning, and the other kinds of uses are fallout, rather interesting collection of fallout, I might add. All right, so I'll leave it at that. This is what relation does. It comes up with a measure from, using one of these measures, it comes up with a coefficient of similarity, which in this case would be 0 to 1, or a coefficient of interaction, again between 0 and 1, and we'll see how that works out in a minute or two. Let me summarize just briefly what we've been talking about for this period of time. We've got a graph as a general model for dealing with problems. It is very good for working with complexity. We can define vertices as any of many, many possible kinds of things, and then we can describe the relationships between those things on a level from very simple to very complex. We can use multivariable relationships using a relation program or some other kind of program that you might have available, and we can decompose the graph that we've found using the VTCon program. All right, now let's switch over to a specific kind of use. And here I want to talk about structured planning, a technique which employs a graph theoretic model specifically in the area of design and planning. Both the VTCon program and relation programs were written with the idea that their major use would be in the area of design and planning. Now, it turns out that there are many other things that you can do with it, and actually in the real uses that have been made of these programs, I would say that even more has been done with things that are other than straight design and planning and have been done in the design area. That's kind of curious, and it's a benefit of always working toward the general. But let's talk about the specific use, because this has a lot of potential for work in the design field. I call it structured planning rather than structured design, really more to extend the idea, to suggest that it's working with concepts and that it applies over a lot of different fields which would use design. What's the problem, anyway, when we get into design fields? What is it that we do? What is the essence of the analysis that goes into a design project? A couple of things. First, we have to identify the problems to be solved, or say it another way, the information to be used, because it isn't always problem solving. In the more general sense, it's what do we do to use information to achieve ends that we're working with. Anyway, it's identify the problems to be solved, the information to be used in a project of some kind. The second problem we have in any project like this is to interpret the relationships between, and now here I'm going to say problem elements, and I'll put it in quotes, meaning the small pieces that we find of a big problem. The idea here is that we can decompose a problem into many different elements, or problem elements. It's very reasonable to assume that. We do that all the time. To interpret those relationships into a pattern for solution. Strangely enough, these things relate very much to what we can do with the kind of model we worked with already. The identifying the problems to be solved, the information to be used, is identifying the set of elements that we want to work with. Interpreting relationships and developing a pattern of solution is establishing a graph, what the links are, and then decomposing and structuring the graph into a model, hierarchical model, which we're going to call an information structure. Let's talk about the problem element idea here. What is a problem element? That's going to be a key piece, I would say, of the whole operation. That is the most important part to be developed for any project. The computer activities that we use here take a rather small amount of time relatively to the amount of work we put into other aspects of problem solving using this technique. Now, of course, they are very important. We can't do it any other way without a computer. But the most important part of it, really, is developing the good information. And so let's talk about what a problem element is. I might also add, these names aren't sacrosanct. We use a lot of different names for the same kind of thing, and it mostly depends on the nature of the project you're working in. Typically, we've called things design factors. That's usually a little easier to stomach for an industrial designer. We're used to thinking about things like that, and that's true also for product designers and engineering designers. Design factors seems to be something that is easy to understand. When you're working at another level, sometimes we call them planning elements. Again, this usually means we're working at a level where there isn't necessarily any physical solution coming up. Could be something which is more organizational or procedural in use. We've also called them information elements, and it's not really too important what they are, as long as you have the idea that we can break up the problem into pieces some way or other, which we can call elements. But this is what we mean by a problem element. An element of information which is important to successful resolution of the problem. It almost sounds too simple. It's not, because there are lots of things out there that we know, a lot of little insights, a lot of information that we get. But it doesn't necessarily have anything to do with the project or the problem we're working on. We have to be sure that which is important, let's get that whole word in there, important, which is important to successful resolution of the problem. It has to have something to do with that particular problem. What are some of the properties that we expect to associate with these things? First, must have design implications. This gets to what I was just saying. If there's nothing that you can think about that comes out of understanding this information that is going to affect what you're doing, then it's not a part of our problem. There are no design implications. Design implication would lead to some change in the way we are developing our solution. So design implications are required. Second, should have surprise. Put that in quotes. You know, what is information? In its stricter sense, information is surprise. If we don't see something we didn't know before, there's no information. We can measure the amount of information in things by how much surprise we have. If we knew what it was before we got it, no surprise, no information. If it's a real insight which changes our way of seeing things, then there's a great deal of information. This is an important idea, because I think sometimes we confuse data and information. Data is just everything you get, and it's really hard to work with that because there's usually too much of it. We have to do something to it in order to make it useful. We have to go through it and find those parts of it which are surprising, which have information. And that's what we actually work with. That's what's going to be a problem element, something which has insight, not just data, roughly. So should have surprise is a very important thing. I can probably encapsulate that in the word insight. Insight is a nice word which covers that kind of surprise we'd like to have in these things. You can't always get that much, but you really strive for it. And a couple other minor points, but necessary. Should be documented. You don't put these things together without the record of where they came from. And 4, should be verifiable. We don't want to use information that may not really be correct. So we need to have some way of knowing whether or not things are really true or really correct, or at least some idea of what how correct they are. So when we're working with something, we don't take it for God's truth if it's not. Those properties are important. Now what we're talking about with a problem element is something that is actually a document, as you begin to get the idea. It's not just a sentence, it's not a word, it's a lot of things all tied together in one page or one record or something that we can call a problem element. Now where do they come from? A lot of different places. Actually what we're talking about is using all the sources that we can find as places to get the information that we need to build ourselves a collection of problem elements. Some of these things are interviews. Interviews are very good as sources for problem elements. When you talk to somebody and they have a good understanding of what they're doing, if you ask your questions correctly, you can cut through so much experience time that you'd have to put in yourself to get at the nuggets of what works or what doesn't work with the kind of environment that an individual is familiar with. The interviews can be tremendous sources of insight. Another one, personal observation. This is harder, takes more time, but for the sensitive eye, personal observation is always good for generating insight. Watch and see what happens. Maybe it's done with more sophisticated equipment than just the eye. You sit down and do television work on it, or maybe you do time-lapse camera work. But personal observation is acceptable. Expert opinion. That's why you pay them so much money. If you get someone who really knows the field, he can again cut through things quickly and give you what we used to call the silver bullets, which go to the heart of the issue and get things down in nice, insightful form that way. Research reports. Boy, everybody ought to have research reports as part of their continuing input in whatever field they're involved in, because all those researchers out there all get down to the end of the paper and have a section called summary, and in the summary they put down those insights that you really want to have. So they're very good. Experiments. Sometimes we have to do this. Experiments take time and they're not always productive, but they're a good source. Hopefully these guys are doing it for you, but you may have to do your own. Again, that can develop good documented information. Surveys. Not always as trustworthy, but you can get information from consumers and the lay people pretty well with survey techniques. And there's, I'm sure, lots of others. The thing is, what we're talking about is there are all kinds of sources for information. And they can all be analyzed to produce the kind of thing we're looking for, which is the problem element. Now, what we're doing is we're building, I won't say a database, since I just got to saying that's not what we want. I'll say an information base. The information base is going to be a collection, probably fairly large collection, of problem elements which deal with the particular problem you're talking about. If you're really working on a continuing basis, they may not only be dealing with the problem you're talking about, but a lot of other problems that you have that you continually work with, and a subset of these at any one time will be what you'll need for a particular project. Let's take a look at what the components are for a problem element. I kind of talked in general terms, so let's see what we really want on one of these things. Then I'll show you a couple of examples. Key components. I'll start out with a few, actually a couple on here that are absolutely crucial and make the nature of this thing very unique. But we'll go through the whole collection and we'll talk about them as we go. First of all, you really need an originator. Somebody has got to accept responsibility for producing the thing. You need that because you got to go back and find what who did it. And quite often you're working with teams or large sources of information, including people all through a company or clients, people. So you need to know where things came from. Second, we need some sign information here. We need a number. We need a name for the thing. We need a date it was done. All this is really just identification information. What do we want here? The numbers can be different numbers. They don't have to be sequential. So let's put that up here, not necessarily sequential. Not necessary to be sequential. For a title, the computer program, both programs that we'll work with, both VTCon and Relation, require a 20-character or less name. So you've got to find some way to short title the thing. And abbreviations are okay. It's just something that will come up, and you'll be able to see it when you get into looking at these things later on. Third thing, influence. This is an important idea. Normally we don't put an influence value in on these until we've established the project pretty well. We've pretty much got all the problem elements that we're going to use. And we go back in and we sort them out on the value of or on the basis of how much influence each one of these has. Now what do I mean by that? I mean a rating on the breadth of effect the solution will have for the project. So you see, some problem elements that you'll come up with are very narrow in the scope that they have. They're really about something very specific, and if you solve the problem well, it's not going to affect anything else. It's just going to solve the little problem. But other ones that you'll develop will be broad in scope. They will, the changes, the alternatives, the possibilities that you have will change the nature of a design or a plan considerably. And those are the ones we want to think about really first when we get into a solution activity. We want to be looking at the ones that are going to affect a lot of change in the system. And that's why we want this influence value on here. We use it can be any kind of scale, I suppose, but usually we use a 1 to 3 scale because it's one of those things that you have a hard time making a judgment on with that great resolution. We'll say 3 would be very broad, and 1 would be very narrow. And then maybe if you feel like it, you can make it a 1 to 5 scale and put a broad and narrow and a, sort of in the middle. The kind of scale you use isn't so important as the fact that you get some kind of scale in here, so we have some means of identifying which problem elements are the most important for their breadth. Next thing, sources. That's key if we're going to be able to document things. So I would say the best form is a footnote form. When you use footnote form, you're working with outside materials, you're going to get pages in, which is important. And many times when you're writing one of these things, you'll have sources, more than one source for the information. So you need to be able to connect it some way or other to the sources, and a footnote form tends to be the best one to use. If you don't know anything else, in other words, it's not something you're getting from a secondary source, or primary source, other than your own work, then you use a footnote form. If it's your own and you have no substantiation other than what you've seen, then use personal observation. So at least we know where it came from. And that's not bad. There's nothing wrong with personal observation. It's just important that we get that in there. Next, E, keywords. Especially if you're working with a computer file where you want to be able to call these up using an information retrieval system. Keywords are important. They should relate to the problem and probably also to solution aspects, as we'll get into in a minute. For indexing, obviously. Recall, index, and retrieval. Next, interactions. Now, we really haven't defined that yet, but there will be interactions between our problem elements. We'll see that some of them are related to other ones. And it would be nice to know which ones are related to which other ones. So we'll put a section on this form which just lets us list the numbers of other ones that are related. But we usually don't do that until we've completed, because we have to run the computer on it for that. So I'll say numbers of related problem elements. Let me abbreviate that to PE. You'll see that enough times here. Probably be easier just to do it that way. PEs. And let me say that it's filled in after computer structuring. Because we'll have to know from the computer work just which ones are related to which other ones. That's fairly complex, as we'll see in a minute or two. Now I'm coming to the ones that are more important. Those are all sort of secretarial functions, really. They keep information about the element in relationship to others and where it came from and so on. But the guts of it, the part that really counts, is a part about the problem and a part about potential solutions. First, about the problem. G is what I'm going to say call observation. That's sometimes also we've used the term insight directly, but I'll say observation and hope it's insightful. And what this normally is a short sentence which encapsulates, or let me say encapsulating, the insight. So you try to distill it down. That's good exercise. But if you can do it, then people can look at it and quickly get the sense of what this is all about. H is also a part of the problem, and this lets us do the rest of it. I'll call it extension. And this is a discussion of everything you can think about related to the insight. Discussion of the facts. Related information. Examples, quotes sometimes. Supporting instances. Anything that you can think of. This quite often, if you're working on paper, will include diagrams and little notes. If there's mathematical information, that can go in there too. This is everything that you can think of to kind of extend and develop this idea of the insight. It normally comes up because somebody reads this and says, what do you mean by that? And this answers what you mean by that. Between the two of them, you get the short strokes and the long strokes. And if you do the job right, you can add a lot of material in here supporting and so on, which really will develop the idea nicely. Very important section. This is a part about the problem. Now we've also got part about solutions. I haven't really talked about that yet, but you'll see why that's involved when we get into a discussion of interaction and how we take two problem elements and decide whether they relate to each other. First part about solution is going to be design implications. I remember I said that you don't have a problem element unless you've got design implications. You've got to have something to do with the problem at hand. Let's make these things general. I'll say operational statements. For how to use the information. Some typical ideas. Now, I'm going to back off and give you some, not only operational statements, I'll really give you sort of classes of operational statements. How can you go about trying to explain to somebody how to deal with a problem? You could say, well, why don't we avoid the problem? Now you see what that is a class of ways of approaching a problem. I can tell you to take this and give me a way to avoid the problem. And you can write an operational statement, as you'll see in a minute, which will do that kind of thing. Another thing I can do is remove the source of a problem. you can think of a lot of ways to approach this. It's a kind of a nice way to think about creativity, really. Remove the source of the problem, isolate the problem. Change the focus. And these are just a few. Actually, there are a lot of ways you can approach that. But what we're trying to do is find operational statements which will tell us how to go about it, how to go about using the information. I would say here, use an imperative sentence format. It seems to work best. You'll see again what I mean. You start out and you say, do this, design that, produce this, create that, change this, something. We tend to use verb forms like this very well when we're trying to think of ideas. All right, so design implications. Now the other piece of the solution part is what we'll call speculations. And that's, again, a word chosen carefully because we're talking about solutions, but actually we're not at the stage in developing this kind of information. We're not at the stage where we're really producing a solution to our overall problem. What we're doing is we're finding spur-of-the-moment ideas, things that occur to us as we go along. And so these are really not, I mean, they are solutions, but they're not necessarily ones we want to use. We got to call them speculative solutions. And so I'll just shorten that and call them speculations. So J will be speculations. And let's see what we wanted to use here. This is working with the design implications, but these are going to be specific ideas. Specific ideas, and they should be well enough formed to mean approximately the same thing to all members of a team. Because in most cases, you're going to be working with a team. And that's where it is when you're talking about difficult problems, complex problems. You're going to have to work with people from other disciplines, people with other experience, even people within your own discipline who can lend a hand, because you need more than one person normally to tackle any problem of a decent size. So we've got to come up with ideas that everybody understands. It can't be ambiguous. We've got to be well enough formed to mean approximately the same thing. And now this is key also. They should be capable of evaluation for other problem elements. And now you're beginning to see something about where we're going. Because what we're going to do is we're going to think up an idea for one problem element, and we're going to test it out to see whether it has anything to do with another problem element. That's how we're going to build this idea of interaction. Let me show you, I'm going to try to get some on the screen here, some examples of these problem element sheets. Now we've done many of these, and I'll try to give you an idea what these look like. This is a full 8.5 by 11 sheet, and you can see here on the upper part of it there's a number, source, place, keywords, originator. Now down here we've got the part which has to, well, I'm sorry, over this part is the part that deals with the problem, observation and extension. And then you see there's a lot of space in here for adding to this information. Then design implications, which are our imperative statements, and speculations, which are noun-like. In fact, I should add to that in a minute. I will as we finish. And then some more things. And here we've put down system functions. In this particular case, we were looking at a problem that needed that kind of statement. Environments that the problem took place in. Down here, evaluation criteria. So you can add a lot more things even than I've suggested here. Here's another one. This was used in a class, Here's a design factor number, and here it's originator, influence index. On the other one, I didn't have the influence on there. That was one we did before we put that kind of system in. Here is related functions. That would be interactions. Or no, I'm sorry, that's related functions like the other case. Short title, really a good idea here. Observation, extension, that's the big part. And down here, design implications and speculations, again, that key piece. And then in this case, sources down below. And we've used a lot of others. These are just give you an idea. You can pretty much get these on one sheet. It's not always possible, but it's close enough. I think we can probably safely say that you can do that. If you need more space, well, then we put more space in. That's all. Use 2 sheets. Let me go back to the speculations and add one more key part here. Here you should use a noun phrase format. When you're trying to get specific about things, nouns help a lot. Usually what we do is put in an adjective and then maybe a noun or a noun phrase, and then maybe we'll tack on, if necessary, we'll put on some modifiers. So we use action for the design implications and then nouns for the speculations. Let me give you an example of what I'm talking about here. It will help. I'm going to take this one from a study we did on ocean systems. In essence, we're talking about marine biology and the problem of collecting and specimen sampling. In this particular case, we're talking about what goes on when a collector, marine biologist, is working at night out on the mud flats or the sand area looking for specimens, which are in many cases just really visible at night. Here's a problem element. So I'll call this one number 1. And the observation is as follows. If 2 people use the same flashlight, only the person who controls it can see clearly what is in the lighted area. Okay, one sentence picks up the inside. You think about it, you probably know about it. If you know, it's crossed your mind before. But it's very important in a project like this, and it may not come out unless it's the kind of thing that you really look very carefully at. Let's see what the extension might be. I've got a copy of it here, and I'll read it, and then I'll put up the key pieces. Extension says a person holding a flashlight anticipates its movement and synchronizes the movement of his eyes to minimize the amount of light-dark accommodation that his eyes must make. Anyone else will lose the ability to distinguish detail, both from the light-dark shifts and the lag time he will experience in trying to follow the beam. So there's several points in there that get picked up in this extension, and they are movement anticipation. Only the person who's got the flashlight can anticipate where he's going to turn it next. Another thing, light-dark accommodation. If you're not following it, then you're constantly in and out of the circle of light, and your eyes are constantly having to change. The person who controls the flashlight doesn't have that problem. His eyes are always accommodated to the light because he knows where it's going to go next. Lag time in following. When the light moves, you have to respond to it, and you're usually always just far enough behind that you never really can keep up with the circle. unless it's being moved rather quickly. Okay, so we got an extension. Now, the design implications, the next important piece. This is all about the problem. What does all this have to do with our project? What design implications does it have? Well, there are two of them in this case. One, enlarge the lighted area. Now, what that is an example of is removing the source of the problem. The source of the problem in this case was the fact we've got these little light areas, so let's remove it. Let's make it a large light area. I don't know how we're going to do it, but that's an operational statement that tells us something we can do to solve that problem. Another thing we can do is distribute the lighting. And that's an example of avoiding the problem in the first place. You don't even have the problem of individual light pools and following and so on if you just give somebody else another light. So we've got light for everybody. So those are two design implications. The next step is to go to the speculation level, and let's come up with a couple of specific ideas. So I'll say 1A here for problem 1, A speculation, will be a lantern. Now, a lantern it follows this, enlarge the lighted area idea. A lantern works very well to do that. To do an example of distribute the lighting, 1B, might be so individual flashlights. Not exactly a major idea, but it works. So these are two speculative solutions. Well, maybe we can find